Science user group. We meet on the first Friday of every month, and our goal is to foster collaboration and learning around data science in the community. So today we're starting, in an effort to foster learning, we're doing a data science knowledge trivia. We're using Kahoot, so as you get your food and find your seat, I encourage you to go to kahoot.it and enter in the game pin, 327467. This should log in. We have 21 players currently. If you're having any issues, let me know. Raise your hand and we can try to figure out what's going on, but it should be fairly straightforward. You go to that website, enter a game pin. Let me tell you about the prizes we're playing for. So we're gonna have 3 winners, so the top 3, and the 3 winners the first place person will get to choose their prize of these things. These are all collectible items from Yahoo, which now has become Oath. So we have a umbrella, we have a football, without air, so you have to put your own air into it. And a notebook and pen. So you can be thinking about, if you get first place, which one you would pick. Now if you're third place, you won't get to pick, you'll just get whatever's left. Okay? So what's gonna happen, we're gonna start in 1 minute. With this trivia contest, there's gonna be multiple choice questions. The question and the 4 choices will appear here, and the 4 choices will each be its own color. And on your device, on your laptop or phone, you choose what color you think. So the answers will not be on your device, only the colors. So, so if you see that the green answer you think is right, then press green on your phone. Or if you think the blue answer is right, press blue. So there's 20 seconds to answer, but the sooner you answer and you're correct, the more points you get. So you still want to be right, but if you can be faster, you'll get more points. So we'll start with a, there's one question that starts that's not worth any points, that's a starter question. Is there anyone that wants to get in that's not in yet? Okay, I will give you guys 24 seconds to log into kahoot.it and enter the game pin. 17 seconds left.
What's the Jeopardy music?
Yeah, we need theme music. You're right. Next month. Oh, so one reason why we're doing this as well, I forgot to mention, this is actually the 10th DSEC meeting we've ever had. So this is a little bit of a celebration. We made it 10 times. So that's big news for all of us, that people like data science enough that we made it 10 times. Yeah, we'll work on the theme music. So if we have any volunteers that want to help out with the music for these events, that'd be great. Okay, so we will get started here. And if you just came here and you still want to jump on, you can, I think at the bottom it'll still say to go to kahoot.it in the game pin. Okay, 11 questions, but the first one's a sample question. So here we go, so this is, you can test out. So it says the question, then it'll say the 4 responses. What are the colors for the University of Illinois? So it gives you 4 responses. On your device, you choose what are the theme colors for U of I. And so there's 23 answers. Again, it's better to guess than to not answer. You get 0 points if you don't answer, you can at least guess. So it's better to guess. 3 seconds left to put your guess in for this question. We'll see how people did. Okay, so just to be clear, on your device you want to choose the answer you think is correct. Okay, so for this question, the colors for our university, the local University of Illinois, is orange and blue. Okay, it's actually not green, yellow, or red and orange. So let's just hope that was a thumb slip or something, that everybody actually knew that orange and blue were the colors of U of I. Any questions before we actually begin about how this worked? Okay. Okay, here we go. Question number 1. Remember, it's better to guess than not answer all. So no one got any points. Okay, so read the question carefully, and the 4 responses will show. You want to answer, if you know what it is, answer as quickly as possible. You get more points. So which method would be best to predict whether emails are spam or not? One of those is correct. Okay, so 19 people got this right. Naive Bayes is the best method for this use case. Okay, and so after each question, it will also share who's winning. So I don't know if this is the actual big dog or if someone used the name Big Dog. We'll see. Okay, so which type of model is best for a churn prediction use case? Better to guess. Okay. So the right answer is logistic regression because it is good for predicting whether someone churns or not, which is a 1 or 0. And so that gives you a probability in the range of 1 and 0. This is good. This is hard. I wanted there to be wrong answers. We always we don't want it to be too easy for you guys. Okay. We don't know if this is the real big dog or not. Which of the following types of models would be best for grouping customers by spend and market? So we're grouping customers here. What would be the best? Okay, 3 seconds left. Better to guess. Okay, you did better on this question. K-means is a clustering model, so that is the right choice here. Okay, a couple more stats questions coming. And hypothesis testing, a p-value of 0.05 indicates, what does this indicate? And a couple of these questions we actually did in previous trivia contests in DSEG. So this was a previous question we used a number of months ago. Read carefully the answers. Okay, so the majority got this correct. Okay, next question. It's a distribution question. It takes value 1 with probability p and value 0 with probability q equals 1 minus p. Which of these 4 distributions is the right one? Okay, looks like this was maybe the toughest one so far. So Grinnell is the right answer. Not binomial. So if there's any protests with the answers, you can talk to our trivia committee afterwards. Okay. So this is a NLP question. Yeah, I think that last one got cut off. This was actually, yeah. So the answers, all of them, are useful. So although I realized there was a little typo here, because object standardization is a valid one, but it wasn't one of the other 3. I'll talk to the trivia committee afterwards, but it still was the right answer. That was valid as well as tokenization. Everything on this was valid. Okay, so which of the following is not considered an ensemble method? So 3 of them are considered an ensemble method. 1 is not. Okay, so a lot of people got this wrong. So a neural network is a deep learning technique, but it's not an ensemble, right? It has hidden layers, but at that point you're not actually taking different types of models to try to have some type of ensemble to see, take values and predictions from multiple ones. So the other 3 will take different types of models or versions of the same type of models and try to use their predictions to ensemble them together. Okay, big dog. We don't know if it's the real big dog. He's not. Professor Bruner's not letting us know if he's actually taking the quiz or not. Okay, if you want to create an interpretable model, show a small number of features, which is preferred? So there's 4 techniques here. Which would be preferred in this case? Okay, so lasso regression is the correct answer. Jordan got that right. Okay, second to last question. What type of deep learning allows dynamic temporal behavior to be exhibited? Okay, recurrent neural network is the right answer. Because it can store data. That's what the word recurrent means. Okay, last question. See if anyone can overtake Big Dog. Remember, we have 3 prizes, so the top 3 are all going home with a prize. Okay, 4th place, you don't get a prize. Just collector's items. Because this is pretty dramatic, the race, especially between 3rd, 4th, and 5th place here. Okay? Just want to bring up the intensity before the last question. This is where we need theme music. You know, like just dramatic music before the final question. Okay, here we go. Which hyperparameters, when increased, may cause a random forest to overfit the data? This is the most challenging question, I think, that we wrote. It's a great last question.
I thought this was about data, not trees.
Okay, the right answer is depth of tree, not all of them. So only depth of tree would actually cause overfitting. So let's see where we ended up.
Yeah, me
Okay. So Big Dog, is that actually you? Okay, so you guys all got schooled by the professor today.
Take my courses.
So if you take his courses, you would do better. So, I mean, this is an obligatory, this is contractual, you have to take a prize, you're one of the 3 winners. Because I don't know who 4th is, it doesn't show.
Who's 4th?
Does it tell you who's 4th? Well, if you really don't want one, 2nd place,
It should say
which was D. Shulman. Who's that? Okay, come on up. Come up, Dan. Congratulations, Dan. Would you like the umbrella, notebook, or football? Perfect. Okay, congratulations. Okay, Mingzi. Right there, perfect, okay. You got the football or notebook? Okay, so the football. So who got 4th place? It should say on your screen if you got 4th place. Like what place you got.
Results.
Well, I don't want to show everyone's results, okay? Because then it'll show who got last. You got 5th? Does it say anyone's phone or laptop say they got 4th? If nobody claims it, we'll give it to the 5th place person. And this prize requires air, so it's probably the worst prize anyway. Oh wait, do we have a 4th place winner? What place? It says top 5, that's all it says. How many points did you have? 5,644, what'd you have? This was wrong, okay, there you go. So you'll need to look somewhere for air to put in the ball. Okay, I hope you guys had fun, learned some things. I'll try to figure out a way to post those questions with the answers just for future reference. We're going to move on now. So next up, okay, that's it. So Ryan is a data scientist over at Oath, Champaign with us, and so he recently had to try to figure out some stuff around doing an experiment for one of our web pages, and in going through that process and figuring out what is an appropriate sample size for this experiment, and he learned some cool things I thought it'd be good to share with you guys. This is more of a stats talk, so you can put on your math caps, and hopefully we'll all learn some things together. So here's Ryan.
Okay, cool. Thanks, Matt. So yeah, just to start, like Matt said, I'm data scientist at Oath, formerly Yahoo Champaign, and I realized that like this, topic title probably isn't the most exciting thing we've had at DSUN, right? Like as data scientists, we're kind of used to like learning about like super cool, like cutting edge, algorithms or frameworks or like technologies, and this is like, stats fundamentals. But I kind of liken this to being the equivalent of like eating your data science vegetables. And like eating vegetables, like real vegetables, this is like super important because you never know when those like stats fundamentals will like rear their heads. And so like Matt like alluded to, this is a maybe not so hypothetical situation. And this is what you're dealing with. So, like your team was tasked with improving user engagement, which is like being measured by like session time per user. And you guys just developed a new like news article recommendation algorithm. And before actually rolling it out, he was like, all right, well, it's time to prove that our algorithm actually does well, right? And so if you're anything like me, when I was asked this kind of a bunch of like terms from like my undergrad sort of like floating around my head, right? Things like A/B testing and hypothesis testing and different sorts of like statistical tests and like their variants, and I couldn't really like bring it all together into like a single actual procedure for me to be able to follow. And so if you're in the same situation, hopefully by the end of this talk you'll like feel empowered with some knowledge of how to actually, you know, follow a procedure and get the number that your manager is asking for. And so just taking it from the top, right? If we're searching for statistical significance, that means you're going to do a hypothesis test. And so it's like most fundamental, you know, what's a hypothesis test, right? You have these two hypotheses. One is the null hypothesis, which is basically that like nothing happened, and the other one is the alternative, where basically you saw some effect, right? But what does like same and different mean? That sort of depends on what your data looks like, right? Same and different, if your data looks like this, means something different than if your data looks like this, or this, or this, or this, and you get the point, right? So this is, you can't read it, don't try to read it. It's a flowchart for what sort of statistical test to use, depending on what your data look like, or what sort of question you're asking. And obviously, we don't have the time to go through this whole thing, so we're just going to focus on one case, right? This like A/B testing example, where you've got two groups that look somewhat like this. And in this case, your null and alternative hypotheses may look something like, your null hypothesis will be that the new algorithm has no impact on average user engagement, and the alternative will be that the new algorithm actually increases average user engagement. And so you can go through that flowchart, or you can just trust me, and so the appropriate test to do is an unpaired two-sample one-tailed t-test. Now most of that I justify why, but the most important one is here, this like t-test, right? What does that mean? So the t-test is appropriate for the comparison of means of normally distributed data when variances are unknown. And I don't know, when I read the normally distributed part, you might have had like a little like record scratch, and you're just like, wait a minute, this is the real world. Like my data doesn't actually look normal like at all. And that's true. So like this up there, that's a histogram of our actual like session times on a user level. So this is like 14 million users or something, just like thrown into a histogram, and it's like hilariously not normal, right? Like this is pretty much as skewed as skewed gets. But what's nice is that you can actually still apply something like a t-test that operates on normal data with this like, you know, neat little trick called the central limit theorem, which you've probably heard of, but didn't really fully appreciate until you actually needed to call on it. And what it says is that basically, if you're looking at like the sum of a bunch of random variates, or you know, sum therefore average, then you can actually use this like statistical magic wand to make it look normal. And so that's like that's the definition. You can read it at another time. But basically, the important part is that this central limit theorem applies almost no matter what your underlying distribution looks like. So for example, even that super skewed thing up there, you can transform into making it look normal. And so if you don't believe me, here's an example. So if imagine that your sampling distribution looks like that super skewed gamma way down there on the left. And obviously not normal, right? And what you're seeing here on the right are distributions of the mean. And the mean is changing depending on how many like samples you're putting into that batch that's calculating the mean. So you only got one. So, all right. So just like bringing it back, like you might be thinking, all right, well, Ryan, you told me that we were here today to talk about calculating sample sizes, not hypothesis testing and statistical tests. And so, just to bring it all together, if you actually want to do what we're here to do today, which is determining sample size, this is like the list of like what we already have, right? So we have normally distributed data thanks to the central limit theorem. We have a statistical test, that t-test, and its associated test statistic. Don't really worry about the equation, we'll go through that later. But we're still missing some components to be able to do this actual sample size calculation. And those two components are error rates and expected effect size. Once you have those, then you can finally get to required sample size. And so I'm just going to tackle those one at a time. So the first one is error rates, right? And so in a hypothesis test, there are two ways that you can basically fail and like be wrong, right? So the first is if you falsely reject the null hypothesis when the null hypothesis was actually true. And that's called a type 1 error, and the probability of that is given by alpha. And the other way that you can be wrong is if you falsely accept the null hypothesis when it was actually the alternative that was true. And that's usually called a type 2, not usually, it is always called a type 2 error and is denoted, and its probability is denoted by beta. And so as part of your experiment design, before you can do the sample calculation, you have to decide like what sort of error rates you're willing to live with, right? So common ones are like an alpha of like 5% and a beta of 10. And those correspond to those critical test statistic values, and later on we can show you how to actually look those up, but sometimes you don't actually need to. But basically, error rates are something that you need to decide on beforehand. And then the second component that we're missing was this expected effect size. So what's effect size? It's really just a fancy way of saying it's the difference in means scaled by their standard deviation. So it's a way of like contextualizing the magnitude of that difference. And this is actually a lot trickier, right? Because if this is something that you need to input to your sample size calculation, it's hard to say how big of an effect you think your change will actually have until you've done it, right? It's sort of like putting the cart before the horse. And so it is tough. Like, I admit this is the really hard part of sample size calculations when they say, well, how big do you expect your effect size to be? There are a couple ways you can get around it. You can just make a guess based on expert knowledge, or you can run something like a pilot study, or what I actually end up doing is that I just calculate required sample sizes for a range of effect sizes, and then see what I think I can get away with. And so just bringing it all together, now that we have all the components in place, just to review, we have this test statistic, right? It's up there, that first line that I can't, is this a laser pointer? I'm not gonna mess with it. All right. And so just to simplify things, we're gonna assume that our standard deviations of our two distributions are the same. And we're gonna assume that we're gonna sample our two groups in equal proportions. That's what S1 equals S2 and N1 equal N2 mean, respectively. And so that simplifies the test statistic a little bit. And so, recall that we have sort of like two conditions that we have to satisfy, these two constraints. The first was that we chose a probability of committing a type 1 error that we're sticking to, right? And so that's this first constraint. This is a constraint on your type 1 error. You're saying, I don't want to be wrong in the type 1 way any more often than alpha. And so that puts this constraint on your test statistic. So it says that you get this inequality by satisfying that constraint. And then on the other side of the coin, you also have a constraint on your type 2 error. And so that's saying that you definitely don't want to commit a type 2 error more often than with probability beta. And that gives you this second inequality. And so what ends up happening is that you have these two inequalities. You can actually do a little bit of pretty simple algebra that all fits on one slide to actually get an expression for n. And so first we're operating on that type 1 error condition. And so you can just rearrange that to express x1 bar minus x2 bar in terms of all of the other variables. And then what you do is you just plug that into that constraint on type 2 error, and you do a little bit of math magic, move stuff around, and then boom, suddenly you've got an expression for n. And so this is what, and just to clarify, so this is n must be greater than or equal to this thing, but because we're not greedy and we're doing a sample size calculation, we're only asking for as much as we need, so we're just going to take the equals and not greater than. And so this is the formula for the minimum required sample size per group for a 2-sample t-test. So the number that you need per group is 2 times t alpha minus t beta, so those are your critical values depending on what you chose as your type 1 and type 2 errors, times the standard deviation of your original, maybe skewed data, divided by delta, which is the difference in means that you're expecting to see. So that whole delta over S thing, that's the effect size D. And so, just as like a sanity check, so you can actually see that this formula makes sense, you can look at it and say, okay, what would actually cause the number of samples that I need to increase, right? So if you decrease the effect size or make the change more subtle, that means that you would need more samples to detect that subtle change, right? So this first bullet makes a ton of sense. And these next two, if you decrease your leniency for type 1 or type 2 error, saying, I don't want to make that mistake 5% of the time, I only want to make it, say, 1% of the time, that means that they're also going to require more samples to do that, right? And so this checks out, like sanity check wise. And so really quickly, just to actually show how this works in practice. So again, here we have the same distribution of time spent. We have 18.4 million users in this horrible histogram, and it's super skewed, it's super high variance, right? So we have the summary statistics over there. There's a mean of about 28, and a standard deviation of 169. And so this is us choosing our error rates, right? So we choose an alpha level of 0.1 and a beta level of 0.2. And since we don't know what sort of expect size to see, we're going to compute it for a range and see what happens. And so just a reminder, there's the formula And those parameters up there won't change. So T alpha will always be 1.28 because we chose alpha to be equal to 0.1. And beta will always be negative 0.84 because we chose beta to be 0.2. And then x bar, that sample mean, that doesn't change, and that standard deviation also doesn't change. And so what you can see if you're looking at, for example, this row that has this percent change in session time of 0.5%. So that's saying we expect the average user session time to go up by 0.5%. What that actually corresponds to in like seconds is that we expect that average to go up by 0.14. What that means, as far as the sample size calculation, is that we need 13 million users per group. Obviously, that's a no-fly zone because we only had, what, a total of 18.4 million. And that's shown here by, we're asking for more users than we actually even have to do this calculation. So if we actually think the effect size will be somewhere in this 0.1 to 0.5 range, this isn't happening. We actually need to construct a new algorithm that'll get an even bigger lift than that. But if you're going down here and saying, well, you know, maybe our new algorithm will have like a 10% change in average user session time, that corresponds to increasing their average time by almost 3 seconds. And in that case, you only need to actually ask for about 0.4% of your user base to be used in the A/B test. But, you know, here's the formula. It's kind of cumbersome. You kind of have to look up what the T alpha and the T betas are. So if you're lazy, like me, you'll actually probably want to use an actual standalone program to do it. So this is something called G-Power, which is actually really nice. So you input your means here, your standard deviations here, that calculates the effect size for you. Based on that, it'll also tell you what those alpha levels are. And what's nice about it too is that it actually shows, it visualizes where your type 1 and type 2 errors are coming from. And so that's one option. And the other option is that if you're like allergic to mice and you just want to use the keyboard for everything, then you can also use R to do this, right? So there's one function in base R called power.t.test that'll do it for you. It'll tell you how many samples you need. And there's also this library called power.pwr, which has, I think, support for more varieties of statistical tests to do these sample size calculations. But yeah, I mean, that's about all I had. I mean, there are some convenient links if you want to actually learn more, but otherwise, hopefully walking through this, I know it was kind of fast, only had 15 minutes, so if there are things that were unclear, like definitely ask me afterwards. But yeah, that's how you can work from like first principles and get down to that formula for sample size. Thanks.
Okay, thanks, Ryan. Thanks, Ryan. Thank you for helping us eat our data science vegetables. And so if you have questions for Ryan, you can talk to him afterwards. We are going to get these slides posted on the meetup group, so you can look for that. So next up, so we have Ed Bukhman here from Altaridey. So he actually is developing his own analytics software, so he's going to talk a little bit about his perspective on the data science world and also just what his software is trying to do. So we'll get him set up.
How you guys doing? I'd like to talk to you about Altaridey, which is, I took some of the insights available to computational and systems biologists and filed those insights, and I'm trying to apply them to time series analysis. So the way this talk is structured, I'll show you a demo first of an interface to this system. And then I'll discuss the theory behind this approach, and finally I'll discuss some applications. Right, so you start on the homepage, altaridey.com. You can follow along if you want. And you go to a beta of an interface, the web interface to this. And the centerpiece of this application is a network graph that relates time series to each other. So we transform from the time domain for various time series to the domain of nodes which represent those time series. Okay, you'll see how it works in a second. And there's two ways to get a graph. The first way is to bring in your own time series, as I'm doing here. Once you bring that time series in, you select some parameters, click submit, and it computes a graph that relates that time series and puts it into the context of all of the time series that the application itself maintains. And that's what's happening right now. So eventually you get a graph, and that graph, the node that you, the highlighted node here is the one that represents the time series that you put in. So remember, the node represents the time series. It's a transformation. So now you can browse this graph in various ways. You click on a node, it shows the relationships between that time series and other time series that we maintain. So the lower pane here, we switch to a different view once you click on a pair of nodes. And the lower pane shows the two time series side by side. And the upper pane shows something called the response function, which is roughly the induced response in one time series in time in response to a perturbation in the first time series that you put. So I'll get into more specifics about what that means in a second. But so you can do all sorts of browsing here and get and learn about the way that time series are related to each other. So there are two ways to get a graph. This is the first way that you're looking at, where you're putting in a time series and seeing how it relates to other time series. The second way, you'll see in a second, is to browse through a list of time series that the application maintains. For example, economic data series or financial data series and so forth. And that's what you're seeing here. I selected a data series that the application has access to. And these data series are live, so there's constantly data coming in from feeds and so forth. So the graph is being refreshed as well. So we recompute the graph at set intervals as more data is coming in and as relationships change between the time series. So that's, so you'll see in a second here where as the graph is updated. But the idea is always to be browsing and to look at the various relationships between the nodes. So this is the recomputation that I was talking about. It's a new, as more data is added to each of the time series, the graph changes. And so the relationships are recomputed, and the features that were previously, as more data is added on the right side, things shift, and the response functions also shift. Okay, so that's pretty much all I had about that. And now I'd like to get into the theory behind what you just saw and try to kind of understand the specifics. So I like this faucet analogy. So we have the data streams. The stream represents the time series as it's coming in, as more data is coming in and pushed into the system. And the faucet is producing that stream. So what you're seeing here in this little animation is the time series. We're transforming from the time series space to this node space. So each node represents the time series. And in turn, each edge in this graph represents a relationship, a statistically meaningful relationship between a pair of nodes. And you can use that information in a lot of ways. You can use it to monitor, as I just showed you in that interface. You can use it for prediction, and you can use it to build control systems. And I'll discuss all of that in a little while. So let's also define what a time series is. It's a very simple definition. You have a sequence of date value pairs, timestamp basically, and a numerical value corresponding to that timestamp. And those date values pairs are equally spaced. So for example, the daily output of tweets by the president, that's a time series. Your body temperature measured at second intervals is a time series, and so forth. And you can those are fairly trivial and well understood, but also things that are not at first obvious as a time series. For example, you can take logging data from your systems log and make that into a time series. If I have time at the end, I'll explain how to do that. So the first step is to determine what the proper edges are in our graph. And we have several ways to do that. The first is simply by computing the correlations between the time series. So we just look at statistical correlations, either synchronous or lagged, and when those correlations reach a certain criterion for significance, statistical significance, we determine that's an edge that we want to accept into our graph. That's one way. The second way is knockout measures. That borrows from systems biology, where you knock out the action of a particular gene in a cell, for example, and see what effect that has on the performance of the cell or on the expression of other proteins in that cell. So we do something similar. We look at a signal at a time series, and we look for strong attenuation of the signal over the course of time. And when we find those periods where the signal, drops very severely, we look at how that affects other time series that we're monitoring. So that's our technique that's another technique that we use. And finally, we use a technique informally called Shazam. It borrows from the Shazam application for music. And the idea is very similar. We take a snippet of a time series and we compute a unique signature of that snippet. And then we compare that signature to the database of all snippets of all other time series that we keep track of in our application. And if we find a match that almost guarantees us that the two series, or at least those two series over the time range of the snippet, are identical. And in fact, the first edge that you saw in my demo was a special, sort of fake highlighted edge. And that's an edge delivered by this particular method. And as you saw, the two time series were identical to each other in that case. So now that we have a set of edges, we want to compute the response. And so we treat our collection of edges, we visualize it as a graph. You can see that here. And now we treat this collection of edges as a gene expression network, basically a physical network where the edges denote activation or inhibition behavior by nodes onto each other or relative to each other. So we set up a set of differential equations, coupled differential equations that determine that on the left-hand side of each equation is the rate of change in the signal in each one of these signals. So there are as many equations of this type as there are nodes. And the right-hand side is derived from the incoming edges into a node. So you basically have a set of equations which you integrate in time, starting from the initial conditions that all of these nodes have zero signal. That's our baseline case. So we integrate that, and then we integrate the same system again, but from different initial conditions. From this delta initial conditions, where we perturb or pulse one of these nodes at time 0 and integrate again. And we subtract the baseline integral from this second or delta integral, and we get something called this residual or induced response. Basically the response that one of these nodes induces in all of the other nodes over some period of time. And that's our response, or that's our measure. That's kind of the final product of this technique of this application. And you can use that, you can see how you can use that problem. The simplest way is, suppose you want to predict one of these time series, how it behaves in time. So the way you would do that is by basically doing so computing the induced response in that time series, which is one of our nodes, and computing that for each one of the other nodes. And the node that gives you the highest induced response, it stands to reason, would have the greatest effect on that time series over that time period for which you're computing your integral. So that's the technique. And a lot of you might be saying, well, how can you map the virtual system of signals to a physical system of a gene activation network inside a cell? After all, this physical cell is subject to constraints which we don't typically have inside of our virtual signals. And I'm not going to give you a full reason, but I'll give you a couple of things to think about, sort of scaffolding for a reason. So the first one is that almost anything that's worth collecting data about, and almost any time series, is mean reverted over some time scale. So that if your network or if your graph is reasonably large, then what you're looking at is a kind of an invariant quantity. If you add up all of the signals, or if you aggregate all of the signals that are included in your graph and add them up in some way, you will see that the overall level of signal stays relatively constant over time. So you can think of the signal as kind of sloshing around the various nodes in your graph, but not really, so it's being conserved, in other words. So that's one reason. And the second reason is that we're using Hill kinetics as opposed to more kind of rudimentary chemical kinetics. Hill kinetics is a biological model for kinetics, and it's more permissive or more forgiving of non-conservation. So chemical kinetics typically enforce conservation, mass conservation, for example, but Hill kinetics are less rigorous in that sense. So they simply express a relationship like an activation or an inhibition relationship. So I want to talk for a minute also about the scaling of this problem. So we can do 1 million pair interactions in about 2 seconds in this application at this stage. But the scaling is quadratic in nodes because we're doing each, so we have to examine each possible pair interaction between each possible pair of nodes. So that's 1,000 nodes in 2 seconds. So obviously, if you want to handle larger models, then you have a problem. So we have a couple of ways to address that. The first way is the Shazam method that I mentioned before. So if you observe that 2 time series have identical signatures over some period of time, you can infer that they may also be identical in the future, so you collapse those 2 nodes into one. So you reduce the dimensionality. But the more interesting and more sophisticated method is based on this paper, which describes how to derive conservation relationships from observations of the physical system. And the idea here, and the idea that we use from that paper, is that we can split our overall collection of nodes into subsets. And the criterion for splitting is that a particular subset of nodes gives us an invariant. Basically, if you aggregate the signals from those nodes over time, the overall aggregation of those signals gives us some quantity that's not changing over time. And that tells us basically that that system is isolated from all of the other nodes that we're observing. So we can treat that system as kind of a standalone separate system from everything else in our graph. And then compute the relationships, or recompute the relationships just for that node. And then everything else in our graph, all of the other nodes in our graph, will be computed separately. So for example, if you split a system consisting of n nodes into 2 using this technique, then you automatically reduce the amount of work that you have to do by 2. So that's pretty much it for the theory. So I'd like to now discuss some applications of this. So as I said before, we have sensors, or in our case it's mostly like financial data feeding into our system. in real time, and we recompute the graph relating these signals to each other, and then you can do a couple of things with that. First, you can visualize, as you saw in the demo, you can simply visualize the graph and browse it. So that's a sort of a very basic application. Next step up from that is a predictive interface. So for example, alarms, where you, and I already sort of mentioned that also earlier in one of the slides, you want to predict one of the variables that you're tracking. And the way you do that is by looking at those nodes, those time series that induce a response in that variable. Once you've found those nodes, assuming they exist, you track those nodes for large perturbations, or at least unusual movements in their signal. Once you find those, those perturbations will eventually work their way into the signal that you want to predict. And so you set an alarm on that. So that's a predictive interface. But there's a problem with that, obviously, because you're waiting for the rare events, the unusual things that would be predictive of unusual perturbations in the signal of interest. So the most advanced application, as far as I think, is a control system application, where you're doing very much similar thing as in the predictive interface, but you make your own perturbations in the signals that are predictive. So in other words, you're not waiting for those signals to change due to external factors, but you're changing them yourself. So control systems, for those that don't know, they're everywhere in life, but the very simple one is a thermostat. You have a variable that you want to control, the temperature in your room, but you don't have no way to control it directly, so you control it indirectly by opening a window or turning on your furnace. So those are the variables that induce a response in the controlled variable, i.e. the temperature. So the same idea here. So we establish the variable that we want to control, and then look for variables among our nodes that are good at controlling it, and use that information to control it, basically, in the same way that we did with the predictive application. So I'm asked, is this machine learning? And the answer is no, because this will repeat the same mistake twice, right? So if given the same sets of data, it will make the same mistake the second time around. Let's actually just discuss for a moment how a machine learning application would work if you wanted to build a predictive analytics model based on the same sorts of data. How would you do that? Well, so you need rare events, which is this action point on our timeline. And events are not happening in a vacuum, so you also need the background, the state of the system, basically the snapshot of all of your time series at the moment when the action took place, or right before. So now that you have this pair, you can measure some outcome, a result that takes place later on. And the range of time that passes depends on the range of time over which you want to make a prediction. So now you do this type of thing a couple million times, maybe more, and you basically map out a surface of all possible state and action combinations. And you have a pretty good idea of what the outcome will be given a particular combination of those state plus event combinations. So that you can now guess, or at least if the surface is, and if the system is not chaotic and the surface is relatively smooth, you can guess the outcome even for an event combination, event plus state combination that you haven't encountered before. So that's one way of dealing with that. And the other way is the system that I described today. So they use pretty much the same data, but they use it very differently. And there are pros and cons to each method. But I actually wanted to get a little bit more mileage out of the cell analogy that I used. So we mapped our graph to a gene activation network inside a cell. And there's another way to think about a cell. A cell, obviously, it's very good at two things. Good at obeying signals sent to it externally, right, from your brain, from your endocrine system, from neighboring cells and so forth. And it's also very good at surviving, as long as it needs to. And so why does it survive? So it sometimes, for the most part, it obeys those signals. But it also is it's influenced by its environment, by its surroundings. So for example, depletion of oxygen or slight elevation of pressure or something like that. The cell will react to those environmental changes. And will react in a way to preserve itself, to counteract those changes as much as possible. It's a very delicate system, so the tolerances are small. Nevertheless, it will react within some band of tolerance. So why does that matter for us? Because by mapping our signal system to the cell system, we can think of any reaction that the cell system has as being conducive to its survival, right? So we can predict how the cell behaves. Its method always is, or its goal is always to survive the perturbation. And it will react by shifting equilibria of the various components of that cell. And that's really kind of how we model our system. We model our system and we can predict what our gene activation network will do because we look at each of these nodes as also part of an equilibrium. So this is, I think that's pretty much all I have. I also wanted to review some of the tech I used. I used TBB and OpenCL for the parallelism in the application and the data processing. And I used Vertex, which is a really nice JVM technology, to implement the infrastructure. And it's the back end to the interface that you saw. So yeah, visit the website, and there's a lot of supporting information there. And please, if you know of anybody who's interested in collaborating, please let me know. I'm always looking to refine this application and make it better.
Okay, thanks a lot to Ryan and Ed for stepping up and sharing today. If you have input for Robert and I for future data science user group meetups, if you have a topic you'd like to hear about, or if you would like to present something, please let us know. We're always looking for more participants from different companies and from different parts of the university to help contribute to this. So we'll be meeting continually through the fall, the first Friday of every month. So the next time is, I believe, September 1st. So thank you for coming out, and we'll see you in September.